Hi and welcome back to freesciencelessons.co.uk. By the end of this video, you should be able to write nuclear equations to show alpha and beta decay. Now, a nuclear equation shows us what's produced when a radioactive nucleus decays. This sounds tricky, but it really isn't if you just learn the rules that I'm going to show you. Let's start by looking at alpha decay. Remember that an alpha particle has got 2 protons and 2 neutrons, so it's the same as the nucleus of a helium atom. Scientists represent an alpha particle by using the symbol for helium, like this. So looking at the atomic number, which is 2, we can see that an alpha particle contains 2 protons. The mass number 4 tells us that the alpha particle has got 4 protons and neutrons added together, so it must have 2 neutrons. Okay, so let's look now at a nuclear equation for alpha decay. This shows the element radium. Radium decays by releasing an alpha particle, and this produces the element radon. Now, you could be asked to work out the atomic number and the mass number for the element produced by alpha decay. So let's work them out for the radon that's produced here. Well, radium has an atomic number of 88, and here it is. So the original radium atom had 88 protons. The alpha particle has got 2 protons, and there they are. To work out the atomic number of the radon produced, we've got to subtract 2 from 88. So that means that the atomic number for radon is 86, and there it is. So this gives us the first rule for alpha decay. During alpha decay, the atomic number decreases by 2. Now the mass number of the radium atom is 226, and there it is. However, the alpha particle released has a mass number of 4. This means that the mass number of the radon isotope produced by alpha decay must be 226 minus 4, which gives us 222, and there it is. So here's the second rule for alpha decay. During alpha decay, the mass number decreases by 4. Here's one for you to try. This shows the alpha decay of the element americium. This is the element that we find in smoke detectors. When americium undergoes alpha decay, it forms neptunium. I'd like you to work out the atomic number and the mass number of the neptunium. So pause the video now and try this yourself. Okay, the atomic number of americium is 95, and there it is. The atomic number of an alpha particle is 2. Subtracting 2 from 95 gives us an atomic number of 93 for neptunium. The mass number of americium is 241. And the mass number of an alpha particle is 4. Subtracting 4 from 241 gives us a mass number of 237 for this isotope of neptunium. Okay, so let's take a look now at nuclear equations for beta decay. Remember that in beta decay, a neutron changes to a proton and an electron. The electron's ejected from the nucleus, and we now call it a beta particle. So this shows the beta decay of an isotope of the element aluminium. It's changing to silicon by releasing a beta particle. Because a neutron has changed to a proton, the atomic number increases by 1. So in this case, the atomic number of the silicon must be 14, and here it is. In beta decay, the mass number does not change. That's because the total number of protons and neutrons in the nucleus stays the same. So this silicon isotope has a mass number 29. Here's the rule for beta decay. In beta decay, the atomic number increases by 1, but the mass number does not change. Here's one for you to try. This shows iodine turning into xenon by releasing a beta particle. I'd like you to work out the atomic number and the mass number of the xenon atom, so pause the video now and try this yourself. Okay, in beta decay, the atomic number increases by 1, so the atomic number of xenon must be 54, and there it is. In beta decay, the mass number does not change, so in this case, the xenon isotope must have a mass number of 131. Now we've looked at alpha and beta decay, but what about gamma decay? Well, in this case, both the atomic number and the mass number are not changed at all. Remember, you'll find plenty of questions on nuclear equations in my revision workbook, and you can get that by clicking on the link above. Okay, so hopefully now you should be able to write nuclear equations to show alpha and beta decay. Hi and welcome back to freesciencelessons.co.uk. By the end of this video, you should be able to describe what's meant by radioactive decay. You should then be able to describe the 4 types of nuclear radiation. I should point out that some of this material can seem a bit complicated initially, but it's not as tricky as it looks, so bear with it. Recently, we looked at the idea of isotopes. We saw that isotopes are atoms of the same element with different numbers of neutrons. I'm showing you 3 isotopes of carbon here. Now, carbon-14 is actually a radioactive isotope, so let's look at what that means. The first key idea to get is that some isotopes have got an unstable nucleus. To become stable, the nucleus gives out radiation, and scientists call this process radioactive decay. I'm showing you a radioactive atom here. As you can see, the atom's giving out radiation from the nucleus, so it's undergoing radioactive decay. Now, a really important point about radioactive decay is that it's a completely random process. Scientists cannot predict when a nucleus will decay. Now, the activity is the rate at which a source of unstable nuclei decay. Activity is measured in becquerel, and that has the symbol capital B, lowercase q. 1 becquerel equals 1 decay per second. To measure the activity of a radioactive source, we can use a Geiger-Müller tube such as this one, and you may have seen one of these in school. The count rate is the number of decays recorded each second by a detector such as a Geiger-Müller tube. Now, I should point out that count rate is not the same as activity. That's due to background radiation, which we look at in a later video. Okay, so we know that radioactive nuclei give out radiation. So let's take a closer look now at what this means. There are 4 different types of radiation which can be given out by an unstable nucleus. The first kind of radiation is called an alpha particle. We saw this before when we looked at the alpha scattering experiment. Alpha particles consist of 2 protons and 2 neutrons. That means that an alpha particle is the same as the nucleus of a helium atom. You don't need to get too bogged down by that idea, but you do need to remember it for your exam. The second type of radiation is called a beta particle. A beta particle is simply an electron which is ejected from the nucleus at very high speed. Now, we've already seen that the nucleus of atoms does not contain electrons, so where does the beta particle come from? Well, the answer is that the beta particle is formed inside the nucleus when a neutron changes into a proton and an electron. The electron is ejected from the nucleus, and we now call it a beta particle. Okay, the third type of radiation is called a gamma ray. Gamma rays are not particles. They're a type of electromagnetic radiation from the nucleus. Finally, the fourth type of radiation that's sometimes given out by unstable nucleus is a neutron. Remember, you'll find plenty of questions on radioactivity and radiation in my revision workbook, and you can get that by clicking on the link above. Okay, so hopefully now you should be able to describe what's meant by radioactive decay. You should then be able to describe the 4 types of nuclear radiation.
In today's video, we're going to look at the terms activity and half-life, and see how we can calculate each of them. We've already seen that some materials contain unstable isotopes, and that in order to become more stable, they can decay by emitting some form of radiation, like an alpha particle, a beta particle, or gamma rays. We call materials like this radioactive, and they come in loads of different forms. If we were to consider a single radioactive isotope, we'd have absolutely no way of knowing when it would decay, because the decay process is completely random. However, if we have a large enough sample of radioactive isotopes, then even though we couldn't tell when any individual isotope would decay, we can still find out 2 very useful things. One is the activity of the sample, which is the overall rate of decay of all the isotopes in our sample. And we measure activity in becquerels, where 1 becquerel represents 1 decay per second. So if a sample had an activity of 600 becquerels, then there must be 600 isotopes decaying each second in that sample. The other important term to know is half-life, which has two definitions, and can be defined either as the time taken for the number of radioactive nuclei in a sample to half, for example to drop from 1,000,000 unstable nuclei to only 500,000, or the time taken for the number of decays, so the activity, to half. For example, to drop from 600 decays per second to 300 decays per second. To properly understand these concepts, let's imagine our radioactive sample as 100 unstable isotopes, each of which can decay by emitting radiation in order to become stable. So if we watch this sample decay, the first thing we notice is that the decay process is completely random. So we have no way of knowing when any particular particle will decay. As time goes on though, and more of them decay, the number of unstable particles remaining decreases. Because there are fewer particles left to decay, this means that the overall rate of decay, which remember is the activity, will also decrease. Which is why it looks like the sample is decaying more slowly than it was at the start. This is why we can define half-life as a halving of either the number of radioactive nuclei remaining, or a halving of the activity. They are both perfectly correlated, because fewer radioactive nuclei means a lower activity. Another way to show this decay process is by using a graph that plots activity in becquerels against time. As time goes on, the number of particles remaining and the activity of the sample will decline. But the rate of decline will also fall, which is why it's curved rather than a straight line. To calculate the half-life from a graph like this, we need to find the time it takes for the activity to halve. So in this case, drop from 600 to 300, which we can see is about 2 hours. And to confirm this, we could check another one by seeing how long it takes it to halve again down to 150. And indeed, it does take another 2 hours, so we can be confident that the half-life is 2 hours. If we had a different radioactive sample though, like this one, we can see that it's decaying much more quickly. This means that it started with a much higher activity, as we can see on our graph, and also that it will decline much more rapidly, and so have a much shorter half-life, this time of 1 hour. Now, so far, we've just kind of assumed that we'd know what the activity is. In real life though, we'd have to find the activity using a device called a Geiger-Müller tube encounter. These things record all the decays that reach them each second. So all of those alpha and beta particles and gamma rays, which it then records as the count rate. And it's this count rate that we use to estimate the activity. Before we finish, let's try one quick question. The half-life of a radioactive source is 40 hours. There are initially 3 million radioactive nuclei in the sample. How many nuclei will remain after 5 days? In a question like this, the idea is to first find out how many half-lives there'll be, and then half the number of radioactive nuclei that many times. So first, we need to take 5 days and times it by 24 hours to get 120 hours. And we can then divide that by 40, which is the source's half-life, to find out that the sample will have undergone 3 half-lives. So then we just take our 3 million radioactive nuclei and half them 3 times to get 1.5 million, 750,000, and finally 375,000, which would be our final answer.